one last presentation for this session. It's going to be Tom Ritz. He's going to present on rehabilitation decisions for MDT's Montana Avenue structures.
Thank you, Nancy, because I gave you a little bit of heartache trying to load this file, and I should have optimized it and minimized some of the JPEGs or something before I gave it to her. So the delay is my fault, not hers or anybody else. Earl, I think you had the joke about the sombrero. I think we're probably going to hear a little bit more about that. That joke's got to come up repeatedly, right? Like, don't design a bridge with your sombrero on, or don't mistake your hard hat for a sombrero, or your sombrero for a hard hat. Okay, again, my name's Tom Ritz. I'm going to talk about rehabilitation decisions for Montana Avenue structures. I think we're just clicking along. I served as a project manager for Michael Baker International, the leadership from MDT, Mike Taylor, the Billings District pre-construction engineer, Thaddeus Lesnick was MDT's project manager, and Tracy Stoner, the MDT Bridge Bureau representative for the Billings District. So what is Montana Avenue? It is a twin structures built in 1960, total of 33 spans, including pre-stressed concrete bulb T-spans and steel spans. I have a bottle of water back there, if somebody wouldn't mind bringing that up. Some of the bridge data. As I said, dual structures, so they are structurally isolated. Total bridge length about 1,700 feet each, so approximately 110,000 square feet of deck combined. This is one of MDT's largest bridges in the state. Some of the original construction I wanted to just make note of. 1960, they had expansion joints at every bend. So you can imagine what that was doing, and spans were somewhere between 70 and 45 feet long. So that's a lot of expansion joints. Those were poorly maintained and leaky. And the original deck was only 6 inches thick and a 1.5 inch concrete cover. So I'm kind of going to set up the situation with where the structure is right now, and then we'll talk about kind of those rehabilitation decisions. So I'm going to kind of move quickly here, but just follow with me. So what to do with these deteriorating bridges? That's what Montana was asking MDT. Now 62 years old and rated in poor condition. You can see the NBI data there on the right for deck, super, and sub, rated 6, 4, and 4. So MDT's challenge. Is it too late to rehabilitate these bridges, given they're approaching their design life, right? That's just around the corner. If it's not too late, what does that rehabilitation look like, and how much would it cost? Question number one. Should they set upon a path to replace the bridges in the more near term, 5 to 10 years? And in that case, what strategy do they need just to get to that point? Third question, or is there a middle ground of proactive repairs, maintenance, and preservation activities? And then in that case, could they squeeze another 15, 20, 25 years out of this bridge? All important questions and all big questions because of the size of the structure. You're kind of going to see some of the defects showing up on some of these pages now. So obviously there's a need to act. We need to answer those questions. They need an informed strategy. And they want to avoid load posting because it's nearing that now. So Michael Baker International was selected by MDT to provide a rehabilitation study. We had a great team. Vector Corrosion Services was a key subconsultant, and 2 subconsultants from Billings, Sanderson Stewart and Terracon. So as I move into talking about some of these rehabilitation strategies, bear in mind, these bridges have already been rehabilitated twice. So just kind of important to note. What were those? 1986, the full depth replacement, 7.5 inch slab replaced the 6 inch, and 2 3/8 inch top cover. Notably, they established continuity over every other bend at that time. So they cut all those expansion joints in half. And they repainted all of the steel spans. The other rehabilitation was 2003. This more of a traditional rehabilitation, I think as we would all think about it. They replaced expansion joints with something better. Waterproofing on the girder ends. Concrete repairs, including galvanic anodes, throughout many of the substructures, 65% as a matter of fact. FRP at a select number, 10 bins. That picture on the left is an FRP wrap. And then concrete sealer on 60% of the bins. Just some of the details as they appeared at that time. Waterproofing, shallow and deep repairs, including the embedded anodes at that time. So 2003, those anodes were embedded, just remember that. So a visual tactical NDT investigation, inspection was required. So we set about doing that. 4 inspectors from Michael Baker, 4 from Vector Corrosion, set siege on the bridge. And it was important for us to gather accurate quantities, because if we were going to give them a good picture of what that rehab cost was, we had to hit this bridge 100% of it, right? Because we had to identify every defect and the quantities of that. Okay. So what did we find? Steel spans in pretty good shape. This paint, protective coating, is 36 years old. Minor to very isolated moderate corrosion. Some of the bearings, an expansion bearing that has an expansion joint leaking on the left, fixed bearing on the right. That's where continuity was established in 1986. Column faces, kind of what you would expect. Lots of delamination, some spalling, section loss. This is a circular column supporting a straddle bent. Has been previously patched, if that's obvious or not, but that is the patch that's peeling off now. More delamination, what you would expect. Condition state quantities, as I said, we captured them all in all the NBI condition states. Some of the pier caps, cracking, spalling, loss of bearing area, again, all quantified. Notably, these 2 pictures are where they established continuity in 1986, and those are pretty clean, both at pre-stressed to pre-stressed spans and pre-stressed to steel there on the right. So condition state quantities, as I said, beams, same story. Very, very different story if it's a fixed versus an expansion pier. These get worse as I go along. Lots of spalling and section loss of shear stirrups and pre-stressed strands. This bottom photo had 9 pre-stressed strands severed. There was 100% section loss on 9 pre-stressed strands. This was not typical. I don't want to overstate that. This much damage was more isolated, but it's still a serious condition. And then these partial depth end diaphragms also just falling apart. So the non-destructive testing by VCS, ground penetrating radar, corrosion potential surveys, and then concrete material sampling, petrographics, chloride concentration, and carbonation testing. Just going to run through some of these. Corrosion potential surveys, quite revealing. An expansion joint, this is the end of a beam, girder end. On the left, where we have an existing expansion joint, and on the right, where it's fixed. The color notation here is from yellow, orange, burnt orange, red is worse. Same thing, potential surveys at the girder ends and columns. Chloride concentration testing was maybe some of the most revealing. These are graphs generated from aggregate conditions across all of the girders, all of the bent caps, and all of the columns. And I think probably many of us in this room know that once you hit 350 parts per million of chloride concentration, that's the point at which you're going to get corrosion initiating in reinforcing steel. So you can see we've got plenty of reach of some of these curves well above that. An in-depth study, obviously, some of the key takeaways, infiltration. Those expansion joints are just wreaking havoc. It's Montana. Lots of snow, lots of ice, lots of chlorides. And incidentally, the bridge was under the management of the city for some 15 to 20 years. And I think their methodology and their frequency of applying salts was very, very heavy at that time. The concrete girders are the critical elements. You saw the most severity there. They have the shortest service life, which we'll see in a moment. And the need to act, right? The cathodic protection done in 2003, we looked at the specifications for those plans. They were 20-year anodes. So they're done. And maybe they were a little bit beyond done because we're seeing repeated damage in the same areas. Projected service life calculations were made. Girders, caps, again, there is the critical area with the girders on top. Less than 5 years. Caps and columns, deck, steel spans. So recommendation categories that we came up with, all this data that we've collected, now what do we do with it? This is now the decision sort of work that we did in hand with MDT to try and give them a cafeteria plan, if you will, but a very, very comprehensive cafeteria plan. So first off, just the baseline repairs. What do they do just as a normal operations? And that establishes a cost datum for us to compare against. So that was reviewed. Infiltration of water, all those open expansion joints, what can we do with them to limit the chloride infiltration? Corrosion mitigation alternatives. This is where the specialties of VCS really come in, and we'll run through some of those. And replacement bridge, it was also looked at. So in red, you'll note the horizon for the rehabilitation was 40 years. Not a small number. The reason we came up with 40 years, in collaboration with MDT, that deck that they replaced in 1986, they're very happy with the condition of that deck today. It's in pretty good shape. And MDT is a big fan of hum-1, treatments, and they've done that over the years. So the expected life of that deck, and they have a polymer concrete overlay coming here soon as well, which is going to give it even more protection, was 40 years. So we thought any rehabilitation strategy's got to survive as long as the deck does, and that was 40 years. That also puts it at 100-year life from its original construction. So the baseline, just basic repairs, same expansion, replace expansion joints as they fall apart, more reactionary, than anything. Repairs every 5 to 10 years or as necessary. Not a recommended approach, of course, but it did establish that cost datum for us. Infiltration mitigation alternatives, so this is those expansion joints that are still there. Compression joint seals were now envisioned for strip seals, and we're going to talk about why that is. It's because we wanted to eliminate as many joints as we could out there. How many could we eliminate with a link slab approach? 70 to 45-foot spans, right? There's a lot of opportunity to even close up more, even when they established continuity in that deck in 1986. So we looked at partial depth and full depth link slabs. We developed a Midas model. We primarily looked at the thermal loading and the braking loading. What could we do with that then? How many joints could we eliminate? That's really what the model was built upon and to answer. At a preliminary sense, right? We're in a study phase, so it wasn't taken to a 90 or 100% degree of certainty. But we're pretty pleased with, I think, the model that we have. So one of the good and better options that we came up with is to create 8-span units or 4-span units out of what's out there today. The corrosion mitigation alternatives. I'm going to just run through these real quick. Waterproofing, patching, metallizing. I think all of us are somewhat or very familiar with a lot of these. There was a coating solution on the fixed vents just to give them a waterproofing protection, silane sealer and or an epoxy. Patch and repair with anodes, classic, right? Classic rehabilitation right there. Survival is really in yellow there. The service life expected, 5 to 10 years with just basic or more 10 to 15 years with patching and anodes. Metallizing, becoming more common, a service life of 10 to 15 years. Discrete anodes, service life quite a bit longer, 20 to 25 years. Overbuild with anodes, particularly when we need to come up or generate some more strength in that particular element. Service life 20 to 30 years. They're getting better, right? They're getting longer. Electrical chemical extraction, ECE, a service life of 20 to 30. This was recommended for substructures as well. Could not be used on the beam ends due to the pre-stressing strands. So what do we do with all this? So at the top, you see girder ends, expansion joints. What we did is with respect to the infiltration, do we leave what's out there today? Every other bent that was closed up in 1986, do we start aggregating spans together into 8-span units or 4-span units? What was the service life of the rehab options, metallizing, overbuild? You can see that in column 1, unit costs associated with those. Now we're getting into comparative metrics and factors, complexity and maintenance. So kind of two different categories here. The girder ends, what can we do there? And then more so in the pier caps and columns. So I haven't talked about the deck very much in terms of the condition of the deck, but as I said, it's in good condition, and that was largely out of our scope because MDT was confident in what it was. They wanted us to focus on the superstructure on down. So we came up with a good, better, and best rehabilitation strategy. Alternative is to create the corrosion mitigation alternatives were combined, right? Because one solution that works for the beam ends may not work for the columns or may not work as well. And certainly ECE could not be used on the beam ends. There was the definition of each of these strategies, I guess is what I should say. So we combined corrosion mitigation alternatives with the strategies in the superstructure to be unlocking that up. And what did that look like? So a good strategy, half the joints in the superstructure would be closed, replace existing compression seals, and use the combination of corrosion mitigation in the table. So caps with anodes and metallizing, and as also stated there, because sorry, I can't read it. And too much data to have all stored in my head. A better strategy, same, we're going to still take half of the joints out and now combine that with a different set of corrosion mitigation strategies that we have in the table. So you can see pier caps and columns, girders, and abutments in that table. Different strategies and sub-strategies for each one. It's starting to get like a lot of combinations of things here, right? And then a best strategy. This best strategy is what we took the entire structure and we only had 3 interior expansion joints. So we have 4 frames or 4 units. Largely, most of those were 8 or 9 span units. We evaluated that in that Midas model. That looked very, very promising. We did not see capacity issues with the columns. Now, bearings would have needed to be replaced in many cases, right? Because we've changed that functionality, that behavior. So with this strategy, jacking cost becomes a large factor to replace some of those bearings. And then the mitigation strategies in the table. These are the comparative factors: maintenance, effectiveness, constructability, life cycle. We set up scoring for all of those good, better, best alternatives that we developed. now scoring them based on those factors. Maintenance scoring, I don't want to get too far in the weeds, constructability scoring, effectiveness scoring, and then also we needed to compare that against a bridge replacement. The replacement bridge is shorter. We had a little bit longer approach retaining wall sections, and it's wider. So we looked at really what would be required for today's standards, not just matching what's there. That wouldn't be fair. What is the replacement typical section that needed to be constructed? So the cost, just about $60 million for the replacement bridge. This is based on MDT's cost data, which might be surprising for that long of a bridge at $60 million, but things are cheaper in Montana, certainly than a lot of other areas of the country. Importantly, how does that cost compare to the cost of the other strategies for mitigation of corrosion? That's kind of the crux of the study then. Cost comparisons. Now we've taken that good, better, best set of solutions and put the price, the cost of those to that. In consultation with MDT, we arrived at a 40% threshold of when that rehabilitation cost became too high. Anything above 40% was seen as too much cost. It's better to go to a replacement bridge structure. I think other DOTs maybe have a different threshold. That's what we decided in this case. And so anything in this right-hand column that was above $23 million was not seen as viable. So what do we do? What do we recommend to the state? We've developed a good, better, best. That in itself is enough to consider and let them, let us, I should say, have a in-depth discussion about what to do. But we had within a good, better, and best, we even had alternatives in there. So it became quite involved, and we came up with these recommendations in each category, but more so the recommendations in the better and the best are where we saw the highest value. So this one, the better option, replacing half of those expansion joints in the structure, looking at the mitigation strategies most applicable and cost-effective with respect to each element, girder ends, columns, pier caps. And then the best option, this one taking that structure to a four-span unit, as I said before. A lot of those expansion joints are now gone in this scenario. We've got some bearings to replace. We've got all the link slab work to get done. This has got a little bit higher price tag to it. That's how we got there. Now, importantly, what I would like you to walk away with is maybe the depth of corrosion mitigation strategies that we combined in those subcategories to come up with a good, better, best. And even trying to do that, there is not an obvious path forward to say, well, this is the only way to do a good and a better and a best. We had even subcategories that are as a part of that. But comparing that against the replacement cost, that's important. There was several strategies there that fit within that that cost threshold of $23 million. And also the do nothing category, right, where just limp this thing along. Is it better to do that and plan for a replacement bridge, maybe 5 to 10 years, or invest that money in a rehabilitation? That's a decision for MDT to make, but as we talked about that, we all saw value and good enough evidence to rehabilitate the bridge using either the better or the best strategy, either one. I think we're comparable. Some of those strategies for corrosion mitigation, though, if we had a particular metallizing, right, which had a maximum year of 20 years, that had to be done twice to get to a 40-year design life. So on and so forth with some of the other mitigation strategies. They may have had to be repeated in the assumptions 2 or 3 times to hit a 40-year design life. That was clear. We all understood that. MDT understood that. How do they get to 40 years? So those strategies had to be repeated. That's all I've got for you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.